Hi, everyone. So excited to be here. I know it's 5:20, so a special thanks to everyone who have chosen to stay longer and not head straight to the happy hour or lunch or dinner, sorry. This is a real dedication, so happy for this. So I promise to make this session worth your time. Today, I'll walk you through how we optimize our EV charging experience at Rivian using AI and machine learning. So Rivian's mission is to keep the world adventurous forever. Quick show of hands, how many of you have driven or drive a Rivian? Awesome, great. For those who haven't tried one yet, I hope the next video will give you a glimpse of what makes Rivian different. As you can see, Rivian's vision is much bigger than building vehicles. We're trying to create driving experience on a scalable platform. This platform approach means new features or improvements, whether it's related to your charging time, longer range, or even new powertrain drive settings, can be rolled out across the entire fleet, not just one model. At the core of scalability is our data-driven development. By using machine learning models powered by real-world data, augmented with over-the-air updates, we are able to ensure that every single vehicle on the road gets smarter over time. That's how we are able to move from Gen 1 to Gen 2 to affordable mass-market vehicles, all while keeping software, AI, and data at the center of our journey. So let's start with why fast charging matters so much. First, for so many EV drivers, fast charging is the difference between local driving and road trips. It enables long-distance trips and relieves the classic range anxiety. Second, knowing how long you will need to charge is very important and crucial because it allows you to avoid idle fees, plan routes better, and actually use your charging time well. But this is not an easy ride. There has been a lot of challenges, especially with charging speed. It isn't just about the station. It's about the weather, it's about the vehicle, the battery, and its chemistry, and even the battery configuration. All these challenges are exactly what we are trying to solve. In short, if you want EV adoption at a scale, you want to make sure that fast charging is predictable and as easy and accessible as possible. This is our motivation and our challenge. As we said, charging experience is the cornerstone for EV adoption. One key aspect of charging experience is the time a customer spends charging their vehicle, whether they spend it in the car or outside. Imagine two customers arriving to the same station at the same time. Both have identical needs of charging 10%. Even though their needs are identical, the time they will take to charge their batteries will be different. This is because the charging depends on several factors. Some of them are short-term, like state of charge and state of temperature of the battery, and others are long-term, like state of health of the battery. At the same time, the weather plays an aspect, environmental condition, and the network itself plays an aspect there. This is a multi-dimensional optimization problem, and it was a prime candidate for a machine learning-based model to augment our existing in-vehicle physics-based model to provide a hybrid solution to enhance our customer driving charging experience. This is the end-to-end charge time estimation architecture. We start with collecting data from the vehicle. All the historical data helps us to develop our features, do model training selection, optimize, and deploy the model. This is a pass on the top. The other passing down there, this is where our real-time data gets passed to a cloud service orchestrator, where we have a streaming engine and aggregation engine. Both of them provide the model with the real accurate input so that the inference is being passed to the vehicle. In this journey, those are all the tools that we have utilized from Databricks. This is our 5 stages for cyclic development in the ML life cycle. First stage, we start with collecting data, doing our exploratory data analysis and feature engineering. Moving from that stage to model training, this is when we use AutoML for rapid prototyping, development of hyperparameter tuning, and loading our experiment metrics. Continuous integration is one aspect here that triggers that step for us. Stage 3 is model registration. This is when we select the best model, we version it, and do batch testing as well. Stage 4 is model deployment, whether it's going to be cloud, edge deployment. Also, how it's going to be rolled out, shadow mode, A/B testing, canary testing. All of those are part of our CD process that's also triggered as part of the overall system. Our last stage is monitoring, and this is when we monitor drift and evaluate for retraining. I'll pass it on to Seehand to go in all the details for all of these stages. Thank you.
Okay, nice applause. Thank you, Mo. So I'll start by starting this journey with you guys to go through each stage. That's my favorite yellow nice. So the first one is data processing, right? For data processing, we think for the whole model lifecycle, it's always defining what's the business need, and then you need to understand, okay, what kind of data you want to take from the system and then ingest it into the model. And from this figure, you can see like half of it is like stopping before the data, right? And I think 60 to 70% of the effort will be focused on getting good data. So a good model, you have to have good data. Or a good data, you may also have a bad model. But a bad data, you definitely have a bad model. So in that case, you need to spend a lot of time to make sure the data we input into the model is good, is gold. So data is the backbone of this model. And to understand how we retrieve those data, like basically for all the problems, you need to understand where the data is from. When you receive the data, how do you process the data? Then how do you save the data? Like where do you write the data? In this case, we utilize the Delta Live table. It's good for batch and streaming and supporting like both strategies. It has linear tracking. Basically, you can know like for each of the data what is upstream table that they are relying on. And it has efficient incremental processing. So every time new data comes in, you're able to process it instead of doing all the historical data at once, which is going to be very costly and time-consuming. Then time travel is very important because if you did something wrong, like in the new version, you can always go back to the previous version and reset it. And finally, data quality. It has a lot of functions saying if you want to check which column is always null, which column is always zero, is the distribution making sense, is it skewed, stuff like that. So on the right, we have these two figures. Talking about what is batch and streaming, because that will be important concepts for our next slides. The first one is for batch processing. What does it mean? It basically means we need to create this specific clear boundary of how do we want to slice the data, right? And we need to slice the data for us, like on a daily basis, like time series level, on a weekly basis, it's important. We want to make sure like each day we get this new data comes in, and we are able to process it and write the data into a table. Second is streaming, which is important if you care more about the event that happens lively. You want the result instantly. So for streaming, it's event-based. It may become one event, 2 events, or more. And then it will go into your processing logic, process the data, and finally write the data into a table. So that's how we understand, okay, you know where you ingest the data, you know how you process the data, and you know where you want to save the data. So the next step is how you govern the data. So we utilize Unity Catalog, which provides us this centralized data governance and management. Then we have access control to see, okay, which layer of data we want to show to other teams, which of layer data we want to just use internally for some development. And finally, you have this lineage tracking. So we have this medallion architecture. If some of you guys have attended the training in recent days, you may be familiar with this concept. But for us, like each medallion architecture have different, like a specific use case. On the very top, we have bronze layer, which is we ingest the data from the vehicle, and we develop this aggregation logic and then we write the data into a bronze layer. So that's like raw data from the vehicle, and we create aggregations like session definition, then we write it. And then it goes to the silver layer where we basically stick a lot of vehicle attribute data, let's say the battery pack or what vehicle platform that is, and it's managed by dbt. It will be appended to the bronze layer data. And finally, we can apply our domain knowledge and apply some aggregation logic of the silver layer data managed by dbt, and finally write the gold layer data into a table. So that's for this medallion architecture. Right now, we have this gold layer data, which can be used by downstream teams for analytics or like machine learning development. Then, after you have, you know where data is from, you know how to write it, you have this medallion architecture to give you, to basically send you to a stage where the data is good to use. You need to make sure you have the job scheduler, because for us, we care about the new data comes in every day, right? So we need to set our pipeline using job scheduler and automate this whole process. And it's mainly applied to the bronze layer. So for job scheduler, there are several functions. The first one is parameter definition. You can define where we want to save the data and what is the environment. Is it testing environment? Is it prod environment? What kind of vehicle fleet we care about? Is it engineering, customer, etc. And then we have task hierarchy and cluster configuration, basically to make sure the configuration of the cluster is right and is assigned to the right team. Then we have data, everything is ready. You have this data coming in the database. You want to make sure the downstream user is able to use it in a very efficient way, right? For me, like I work on machine learning, every time I do the model, I need to make sure when I query the data, it's fast. So we utilize liquid clustering. So liquid clustering replaces table partitioning and Z-order to simplify data layout decisions and optimize query performance. It provides the flexibility to redefine clustering keys without rewriting existing data, allowing data layout to evolve alongside analytic needs over time. So liquid clustering applies to both streaming tables and materialized views. So for us, I think it's up to 4 columns of the partition keys, cluster keys we can apply. So for us, maybe sometimes we do it on date, and sometimes we apply the keys on event. So right now, you have a job scheduler. You have your data easy to query, and then it's the time for the real story, right? So I want to share a personal story, but you guys can keep looking at the slide. Last year, I was doing a road trip in Maine. If you guys don't know where that is, it's close to Canada, super cold, December, right? So what is Maine famous for? Does anyone know that? Did I hear lobster somewhere? Okay, that's a good answer though, but I don't agree. So it was famous for lobster, and I was craving one after a road trip on a daily basis, right? So, but I was driving an EV. I need to plug in for my day trip tomorrow. So I went to Hannaford, which is like a local grocery store. I plug in. There's a fast charging there, but the EV I was driving is not Rivian, just disclaimer. So I saw the time was like 20 minutes, so I thought, okay, I can go in there, get a lobster, and get it steamed, and buy a bottle of Chardonnay, and then just come back to my hotel and enjoy some Netflix. But when I came back, I paid everything like around 20 minutes. It still shows 20 minutes left. I was like, did I time travel or something? But no, right? It's because like it's not accurate, and I have to base on that number to plan my trip. So that's why having an accurate charge time estimation is important. And my story kind of covers all the factors here, if you see. So charge time estimation is consisted of holistic factors that we can see in the vehicle. Includes vehicle attributes, including battery voltage, current, temperature, and the state of charge. Also environment factors like temperature, and finally the charger factors, like what is the pin temperature, what is the charge current limit, stuff like that. So the reason that in my case it was not that amazing is the system needs to ramp up at the beginning of the charging, and a lot of the prediction it gives is not that accurate. So we want to include all these holistic factors, including the battery temperature, like the environment scenarios, and also the charger situation, all together give the user a more accurate charge time estimation. So feature engineering is very important. We need to understand our data. We need to do EDA. We need to make sure that the columns we are importing into the model is relevant to this issue. And then right now, we have done data processing. Next up, following the beautiful yellow R1S, we are going to do model training. So every time we have a machine learning problem, we need to make sure that the data we input is going to be, like the data we use or this project is viable, right? We don't want to just deep dive in it, work on something, use irrelevant data or some model, and then there is like the evaluation metrics or the performance of the model is not good. So for this agile and fast test proof of idea, we utilize AutoML. Basically, we can import our data set in there and define our target column and see like whether the output is good. So I'm just walking through like AutoML like to see how it works. So after you define the experiment, you are able to see this kind of report. So on here, if this clicker is working fine, okay. So you can see how long you wait, let's say 2 hours, and then what's your evaluation metrics, and then what's the run name, what is the data set used for the model, what model it uses, and what's the evaluation metrics over there, right? Most importantly, we will have this view notebook for best model, and also those notebook. So we are able to utilize those notebook because the notebook has a lot of functions. Basically, all the functions from what I listed there is in this one script. And I find it super helpful. But a lot of those could be recycled if we have, let's imagine, because this will just be specific to just one topic, right? If I have more projects or I want to test another model using different data, then I have to tweak it myself. But to make this whole process more agile, we have this function modularization process where we take a lot of functions in the script that could be recycled, reused, and then make into utilities library. So it includes preprocessor utilities, library patching utilities, feature importance, and logging utilities. So after we modularize all those functions, they are very easy to query and easy to define, so we can make this whole thing very generalizable to other projects or other models. And for other projects, let's say we have a new model, we can just simply call that and redefine our own training testing data split, our own preprocessor logic, our own objective function. So now going into training, because from the AutoML, we have a general idea, okay, the project is working. The evaluation metrics from the output is great. And we know, what's the initial standpoint of the hyperparameter space we can have there. But if we want to make the model even better, we need to do some DIY ourselves. The first most important factor is hyperparameter tuning. So on the top right, you will see there are like 3 basic strategies. First one is grid search. Basically, you just loop through all the combinations and then find the minimum value, the optimized value. Then second one is random search, and third one is Bayesian optimization. And for the advanced strategy for hyperparameter tuning, we have hyperopt, optuna, and retune. So I have listed some of the pros and cons there. Maybe like you can have a broad understanding of if you are working in different industries, which one is the best for you. So when comparing hyperopt, optuna, and retune, each has its strengths depending on your use case, right? Hyperopt is one of the earlier two and supports search algorithms like TPE and random search. It has basic pruning support and is relatively simple to use. Make it great for quick, straightforward experiments. Optuna builds on that with a more modern design. It's very user-friendly and supports advanced search methods like multi-objective optimization. It also comes with built-in pruning and visualization tools, which makes it ideal for research and prototyping. On the other hand, retune is built for scalability. It supports many search and pruning strategies, including those from hyperopt and optuna, and allows for seamless distributed parallelism across CPUs, GPUs, and clusters. It is most flexible, but requires a bit more setup. So in short, if you have a simple job, maybe you can go for hyperopt. If you want to just do it fast and for experimental, optuna is your friend. And then finally, if you want to scale your tuning into production level, maybe you can try retune. That's for hyperparameter tuning. And we will have our hyperparameter space defined. So next step, we'll go into the deep dive of model training. So this is the whole pipeline layout. I'm just going to quickly go through it. The first one is column selector. That means, maybe in the system, you export thousands of signals, features to a model, but your model needs to know which features are relevant to this issue, right? The model needs to know, you go into the system, which columns you are going to grab. So that's the column selector. And then you will have the transformers. Basically, you have different data types, numerical data, categorical data, Boolean, or date. It needs to be transformed into a certain format for model training. Finally, combining all those transformers, we have the preprocessor. And then we can dump the data into machine learning model, and then we do hyperparameter tuning, and we try to optimize the objective function to find our best model. Best model, yeah, on the right. But it's always important for the machine learning development is you have to save all the artifacts, like what the model is consisted of, like the attributes, right? You need to save your, that's why we are saving, what's the feature importance of all the features, what is the training data, what is the validation data. And those will be reused in the future, and we are gonna talk about that in the following slides. So now we are done with model training. We can run our experiment and train our model. So next step, following the RNS, we have model registration. So here is a bird's eye view of model registration. You can see on the very left, we have always those experiments. And what experiments mean is basically the slides I shown before, is you have all those model trainings, and for each experiment, you have the hyperparameter space defined, and under the experiment, it's going to try out all the combinations of different hyperparameters to see which model using the same data is going to give you the most optimal result. So for each experiment, you have a bunch of model logged in there, and each of the model, using MLflow, we are able to see what are the evaluation metrics, how the model performs. And then based on the evaluation metrics we define, let's say some people are interested in MSE, mean square error, some are more interested in the MAPE, mean absolute percent error. So depending on what kind of objective function you define, you can find your best model for each experiment. So each experiment will output at this stage the best model, right? And the best model is selected from all those trails. And then, depending on your use case or you tested it on some data, you can do some registration. Let's say you see this best model. You want to register it. You want to keep it. So that's where the versioning comes into the play. So you want to version this model saying for this project, for this specific task, for us is charge time estimation. We have like first experiment, this hyperparameter space, like the best model we have it, that's version 1. And for others, maybe we tweaked our input, we tweaked our feature data, and we switched our training test strategies, or we have a different hyperparameter space, that'll be version 2, etc. So you can have all those versions of model registered in Databricks environment, but those are auto-winning models, right? Like those are best model from the experiments. How do you select? Like which one do we decide on to be customer-facing? So we need to make sure that when we compare the model performance, it's apple-to-apple comparison. So we always use this kind of a batched aggregated data, which are super helpful for us because it's always the data that the model, like any of those models, haven't seen before. So that's the new data the model haven't seen, and then the new data will be applied to each of the model. In this case, evaluation metrics for each of the best model will be ranked. So it depends on, are you care more about, like what kind of evaluation metrics you care the most, or you care more about generalization, or like some accuracy, the raw accuracy of the model. You can rank them, and then you can find your prop model. So the SpongeBob is pretty happy, it's cheering, but I think it's cheering too early because we are just halfway through. The first stage is model deployment. Okay, so right now, from the previous step, we saw the best model, like the champion model from all the experiments, right? And we say, okay, it's ready to deploy. We have this prop model. Databricks makes it easy, so we can use the serving endpoint feature. And we can select, the first one is your entity. So what entity means is what model registry you logged all your model in, like, and then it's basically a folder. And then you can select all the versions that you saved in the previous step. So after you find maybe version 7 is the best, then you just put version 7 over there. And then define a compute type, and then assign concurrency. So for concurrency assignment, it will always require some domain expertise or some insights from the fleet data. Because that means, every second, how many users do you expect to call your model? I say, if you run a social media company and you know you have thousands of users or even millions of users, each second you may have thousands of users using this service. So you really need to scale up your concurrency. But you're not sure, like, is it going to be enough, or you're not sure like how many users is going to use it. You can start with a small number. So in this case, we are able to deploy our champion of the champion model into this serving endpoint. And the model will be there. And then we need to understand, like for future monitoring, we need to make sure that we are able to see what is the input, what is the output of the model. So in this case, we always activate this function called enable the inference table. And this will give us the flexibility and also availability of what the user inputs into the model and what the model actually predicts. You just need to define your own schema of the data, like at the very bottom. On the right, you are able to see what kind of attributions you can define using this service. You get from the live reference table. The live inference table. Includes includes like what date the model was called, what's the timestamp of the model was called, what are the request input features, and what are the output features of the model. So having all this data information set up, we are able to retrieve our model for performance, like for future monitoring work. And finally, I mentioned sometimes you care more about accuracy, sometimes you care more about generalization. So in this case, you want to do A/B testing. You're not sure which model to deploy. So you're able to do the traffic split for A/B testing. In here, you can add a served entity and basically assign different traffic on those blocks, saying if you have two models, maybe each one 50%, and then the downstream inference table, you'll be able to see what is the model that you are using when the user calls it. And also, you are able to query some of the models if you want to do a baseline. If you're working language model, if you do want to do a baseline comparison, you can always compare your own fine-tuned model with other baseline model there to see whether your fine-tuned model is actually improving. Okay, so after you have this whole setup of serving endpoint, and it's there, and customer starts to use it, or it's in shadow mode, we are able to monitor what is the latency of this model. Basically means how long the user has to wait before the event is triggered and then they get the response from the model. And on the right, you are able to see what's the request rate. And based on the request rate, you can go back to concurrency definition to see, do you need to increase it, do you need to decrease it? Because if you have your concurrency set up to a very high number, it's extra cost. But if you see, okay, it's not actually that commonly used, maybe you can shrink it down a little bit to save the cost. So that's the cloud pathway, for serving endpoint deployment. You have the model deployed on the serving endpoint. Then we need to make this communication between the vehicle and the endpoint, right? And this diagram shows a bird's-eye view of how we implement this communication. So our definition is always when the vehicle is plugged in and charging starts, the vehicle will be able to know what kind of feature it will look into. So we aggregate all those features within a certain time window. And if there's any null values, because in the vehicle there could be situations happening. And if there's any null values, we have this fleet generated NA reference data, which will be used to fill in the null value. And then you have this complete data set. We'll convert it into a JSON format and use the REST API called the serving endpoint API, calling the serving endpoint model. And the input will be registered into Databricks inference table, and then also to the vehicle and to the user. So this is for cloud pathway deployment. And some of you guys may ask, okay, because Rivian, our commitment is to keep the world adventurous forever, right? And what if you are in the wood, you're isolated, you don't have internet? What does the user still have this service? So for Onyx, that's what we use to resolve it, to edge deployment. So to deploy machine learning models efficiently on edge devices, we need a lightweight and interoperable across platform service, which is Onyx, or open neural network exchange. So it serves exactly the purpose of the lightweight and flexible service. It provides a standardized format to represent models trained on various frameworks like PyTorch, TensorFlow, or XGBoost. So they can be executed on resource-constrained environments such as embedded systems, mobile services, or in-vehicle controllers. Converting a model to ONNX enables hardware acceleration, reduces inference latency, and ensures portability across different runtimes. This step is very important in production pipelines where low latency and platform independence are key to real-time decision-making at the edge. So how do we do it? Our next slide shows, our model is not just a regressor, right? And as I mentioned above, like there's a complete pipeline. So it's consisted of the column selector, the function transformer, and like inside of it you have the imputer, the standard scaler, and then the regressor. So for ONNX conversion, we have to convert everything. And that's circle back to the point where we say, okay, when you register a model, you have a model, you need to make sure you have everything that model is consisted of available. There's the training data, validation data, feature important and stable, etc. So we are able to retrieve the training data that we use to train the cloud model and basically imitate this whole process for each of the previous steps in the pipeline, and then refit those steps into ONNX format. And plus the regressor ONNX conversion, we are able to convert this whole pipeline into ONNX format. So in this case, we have our cloud pathway defined, and we also have our edge pathway defined. Then finally, exciting stuff, monitoring. You have our model deployed, you want to see how it works, right? So what are we monitoring? Most importantly, we want to supervise all those drift. Data drift, label drift, and how those are caused, because the seasonality maybe when we train the model it's warm, and when actually like in the winter it's cold, the distribution of data when you train the model is different. And there could be a new emergence of new charging network, which becomes like very fast being the dominant, and then basically the charging profile is different. So the input features distribution are different. And maybe our user behavior is different. Like a lot of users starts to have more top of charge, they charge 100%, which will be relevant to the data charge time performance. So data drift, label drift is very important. Label drift is how our target variable is the predictor could change. And that can be caused by, on the right, you will see the upstream software update, including, there's a battery performance update, or the current profile is changing, or there's like a new vehicle platform or a new battery pack. So combining all these two together, we need to make sure our model is generating stable and accurate statistics. So fleet prediction, offset statistics is the one that we are actually monitoring to make sure, okay, what is the prediction offset across a week or across a month or across a certain time frame. And then we also monitor model latency, how fast the user get the response, is there more lag than before. And then there's maybe software and model input-output discrepancy, because maybe what model outputs there and going down to the software, there's a misalignment there, and we need to understand why. And finally, how often do we see the no connectivity issue? So based from this monitoring system, we do have some real-life challenges, and this is a real case. So if you guys remember, this plot is what I showed before on the medallion architecture, right? And this data is all used for training data, and they're all based on cloud. But for this training model, it's not always perfect, because it's different environments. Like cloud environments, like data we receive could be different from the environment in the vehicle. To resolve it, like cases where vehicle signal have different sampling rate or not enough data getting populated, we are utilizing the inference table in Databricks, because that's what actually in the field the input will be. So we're concatenating what we see on the fleet into a new set of training data, plus the cloud data, because cloud data still have massive value. So combining those together, we have this improved training data. And then this improved training data will go down into this cyclic development through data processing, model training, registration, deployment, and then we need to monitor it again. So with all those in mind, we have our exciting results. The first one, definitely, we are having this accuracy enhancement by at least 10%. And second of all, which is we are super proud of, is this machine learning project is driven how the product is designed, right? So we are able to give the flexibility of the user to understand how long it's going to take for them to charge to different steps of their of their charge bar. So before it was only, you have setting to 80%, then you only give you one number. But right now we can understand if your setting is 80, but if you we can give you the output is saying if you charge to 60 to 50, like how long it's going to take. So you can better plan your route. And then we provide a significant amount of internal insights on higher granularity charging behavior and on features beyond physics-based simulation model. And also, if there's anything happens in the model, we see on our backend there's any error. The integration is very agile, it's very fast. So the seamless integration, we can do it with minimal disruption. And here's the actual product. This is Rivian Energy App 2.0. On the left is what you see on the charging panel. Okay, so it's idle, so you're not charging actually. You can see here what is your current SOC, state of charge, and what is your setting if you start to charge. But on the right, if you plug in to a charging station, you're able to see where you stand. That's a green bar, and also the gray bar is what the future charging will happen and how long it's going to take. Also, this curve can tell you what is the energy output input from the vehicle and the charger. So this is really exciting, and the result is good. I'm going to hand it over to Mo to wrap it up.
Awesome. Thanks, Ian. So what is next? We want to scale our edge deployment. I think this is a great example of a problem where physics-based and AI and machine learning together could develop a hybrid approach that could solve one of the problems that's related to batteries, charging, and overall EV adoption. So edge deployment is a great opportunity for us to tackle. Second is using that workflow that has been already set up and scaling it to other problems as well is our second step. Third is that we're growing the team within the company. So for all of you guys, please feel free to scan the QR code and join our team. Okay, that's a disclaimer that the content presented here is for informational purposes only. And for more accurate and current information, please refer to the official Rivian communications. So yeah, finally, please take a moment to fill in your survey. Thank you. Any questions?